Welcome to the deep dive. You ready to dive deep today?
Always ready.
Awesome. So today we're looking at AI scaling laws.
Okay. Yeah.
And we've got this stack of research papers. It's really fascinating stuff. They're exploring how AI capabilities actually change as we make these models bigger and train them on way more data. It's like, are we going to crack the code of AI intelligence, figure out how size and data equal smarts?
Yeah, and I mean, the really cool thing is researchers have actually found these patterns, these scaling laws they're called, and they show us that there's actually a predictable relationship between how big an AI model is, how much data it learns from, and how well it actually performs.
Okay, so it's not just about making AI bigger, it's about finding the recipe for intelligence, right? Are there actual formulas or equations that govern this? I mean, how does this work?
Oh yeah, absolutely. One of the biggest discoveries has been these power law relationships in AI performance. So these power laws, they basically tell us that when we increase certain factors, like the size of the model, the amount of data we feed it, the compute power, the AI's performance improves, and it does it predictably.
Power laws, those are wow, the blueprints of the universe or something, right? Can you give us an example? How do these power laws actually play out in AI?
Okay, sure. So there's this formula. It's for determining the optimal learning rate, like how fast the AI should learn. And it looks kind of scary. It's like ND, ND, Eshneen, but basically it tells us how quickly the model should be learning based on its size, that's N, and the amount of data, D.
Okay, I'm seeing letters and symbols. What does this actually mean?
Well, it means we can predict, pretty accurately, how much we can improve an AI's performance by, messing with these factors. Imagine a recipe, It tells you exactly how much flour and sugar you need to bake the perfect cake.
So we can use these power laws to fine-tune the AI's recipe for learning. That's wild. But does this mean we can just keep scaling up AI forever and it'll just keep getting smarter?
That's a great question, and it's where things get really interesting. These scaling laws are powerful, but research shows us there are limits too. We can't just assume bigger is always better.
Limits. Well, hold on. So even if we had all the data in the world and infinite computing power, there's a ceiling to how smart AI can get. What are these limits? And how do we even know they exist?
Researchers have observed these limits. One study, they used this large language model called Quinn, and they were looking at scaling up reinforcement learning training, how the AI learns from experience. And at first, they saw these huge performance improvements as they increased the model size, the training data, all that. But they eventually hit this bottleneck, a point where scaling it up further didn't really lead to any more gains.
So they were pushing the AI to its limits. Imagine a marathon runner trying to, I don't know, shave a few seconds off their best time, and they hit a wall.
Exactly. And it wasn't even like they needed more data or more compute power. The researchers actually thought that the bottleneck was because of limits in the base model itself, its actual reasoning and exploration capabilities. Imagine trying to teach a dog advanced calculus. Their brains they aren't wired for it.
Okay. Yeah, that makes sense. You can only push a system so far before you hit its fundamental limits, right? So does this mean we've hit the peak of AI intelligence? Are we stuck?
Not necessarily. This is where things get exciting, I think. Scientists are looking at all these different ways to break through these scaling limits. One idea that's pretty promising is exploring different architectures for AI models. Things like sparse architectures.
Sparse architectures, what is that?
Okay, imagine this massive library filled with books. Now, a traditional AI model would try to access every single book for every single task, even if it only needs a few pages. That's super inefficient, right? But sparse architectures, they're different. Take mixture of experts models. They're called MOE models. They're designed to activate only the parameters that are needed for a given task.
So it's like having a team of librarians. Each one's an expert in something different. You wouldn't ask the librarian who specializes in, I don't know, ancient history to help you find a cookbook.
Exactly. MOE models, they're designed to be way more efficient by only calling upon the right expert for the job. And the cool thing is that those scaling laws that we see in traditional dense models, those still seem to hold true for these sparse MOE models.
So even though they're more efficient, we can still use these power law formulas to predict how they'll perform. That's a seriously useful tool. But are there other things beyond size and architecture that affect these scaling laws?
Oh yeah, there are. And this is where research is still developing. Things like how good the data is, the training methods, even the specific tasks the AI is trained on, it can all make a difference.
So it's not just about crunching numbers. It's about understanding the nuances of how AI learns, right?
Yeah, exactly.
This is so fascinating, but it feels like we've only scratched the surface.
We definitely have.
There's so much more to explore.
And we will. In the next part of our deep dive, we'll go even deeper into the limits of scaling laws and explore some of the newest research that's pushing the boundaries of AI intelligence, like beyond what we even thought possible. So stay tuned. Welcome back to the deep dive.
So we've been talking about these AI scaling laws, and now we're going to uncover even more about just how robust they are, and like what factors influence them.
It's so crazy to think that these patterns, these relationships between the size of the model, the data, and the performance might actually stay true even when we change the fundamental building blocks of AI. And that's exactly what researchers are finding. One study, they actually looked at whether these scaling laws would still apply if you change the AI model's actual architecture. It's called topological features.
Topological features, okay.
Yeah.
Can you translate that from AI jargon into like normal speak?
Haha, sure. Think of it like the blueprint of the AI's brain, It's like how different parts of the model are connected and organized. And this study, it looked at what happens when you tweak that blueprint, like what happens when you change things like how many layers are in the model or like how those layers are connected.
So they're basically rewiring the AI's brain and then seeing if these scaling laws still work. What did they find?
It's pretty remarkable, actually. They found that the scaling laws for figuring out the optimal learning rates and batch sizes, those stayed consistent, even when they significantly changed these topological features.
Wow, so that means that these scaling laws, they aren't just specific to like one type of AI model. They might actually be like a more fundamental principle of how all AI systems learn.
Exactly. And this robustness, it goes beyond just architecture, too. Another really key finding is that these scaling laws, they seem to be robust across different types of data as well.
Okay, so it doesn't matter if we're feeding the AI text, pictures, sounds, these patterns are still there.
Yeah, precisely. The researchers actually, they tested their models on all these different data sets, like different sizes, different domains, even different modalities, like text, images, audio. And they found that those scaling laws, they stayed surprisingly consistent.
That's a huge step towards like developing truly generalizable AI systems, right? Like we could be on the verge of actually understanding how intelligence itself scales,
Yeah.
regardless of like what specific information the AI is learning from.
Yeah, it's a really fascinating possibility. And remember the sparse architectures we talked about before? The ones that only use certain parts of the model for specific tasks? Well, that same study, they also wanted to know if scaling laws apply to those too.
Okay, so they're testing if those librarian expert teams that we talked about earlier, if they still follow these predictable scaling patterns.
Yeah, exactly. And what they found, it was really remarkable. The scaling laws for dense models, they were actually surprisingly effective for predicting how those sparse MOE models would perform as well.
Oh, wow. So even though those MOE models are like inherently more efficient, we can still use the same formulas to like figure out how their performance will change as we scale them up.
Exactly. Precisely. It just strengthens the idea that these scaling laws, they're like a deep principle that underlies AI learning. It extends beyond specific model architectures or data types.
This is also promising, but I think it's important to remember that we're still like really early on in understanding these scaling laws. Like what are some of the limitations that researchers are still trying to figure out?
Yeah, that's a great point. One key limitation is that these scaling laws, they mostly focus on quantitative aspects of performance. Like they can tell us how well an AI is going to do on a specific task, but they don't really tell us about the qualitative aspects of intelligence, like creativity or adaptability, common sense, things like that.
So we can predict how well an AI can, I don't know, solve a math problem, but we can't predict if it'll like come up with some groundbreaking new theorem.
Yeah, exactly. And that's really where the next frontier of AI research is. It's developing models that not only scale in performance, but also show those more human-like qualities that we associate with real intelligence.
So we need to move beyond just the numbers and start looking at like the more nuanced parts of AI intelligence.
Yeah.
How are researchers trying to tackle that challenge?
Well, one really promising area is developing what they call slow thinking AI models. These are systems that are specifically designed to mimic those really deliberate step-by-step reasoning processes that humans use when they're solving complex problems.
So instead of just those lightning fast calculations that we usually think of with AI, these models are like designed to think more slowly and deliberately, like a person who's really carefully analyzing a problem.
Exactly. And one study, they used this model called Quinn, and they found that by scaling up the reinforcement learning training, they could get some pretty impressive results on these really challenging tasks, like math competitions.
So they were training these slow-thinking models to like tackle these super complex problems that require that, careful reasoning. Did they find that these models followed like the typical scaling laws that we've been talking about?
Well, at first, yeah, they did. As they scaled up the model in the training data, they saw these, big performance improvements. But just like in those other studies we were talking about, they eventually ran into a performance bottleneck.
So even with those like really carefully designed slow-thinking models,
Mhm.
there was still a limit where just scaling up the training didn't really produce any better results.
Yeah, exactly. And this is where the researchers started to look more closely at the limitations of scaling laws. They actually thought that this performance bottleneck might be because of limitations in the base model itself, like its fundamental ability to reason and explore.
So it's like trying to teach a kid to write a novel before they even know the alphabet. Like no matter how much you try to encourage them, there are just some basic skills that need to be developed first.
Precisely. And this highlights a really crucial insight. Scaling is just one piece of the puzzle. We also need to focus on developing AI systems with stronger cognitive foundations,
Yeah.
systems that are better equipped to handle those really complex high-level reasoning tasks.
It feels like we're starting to unlock the secrets of AI intelligence,
Yeah.
but there are still so many mysteries to solve.
Welcome back to the deep dive. So we've been digging into these AI scaling laws, and we've seen how powerful they are, but also that they've got their limits.
Yeah, like we're finding those fundamental rules for how AI intelligence scales, but those rules, they don't tell the whole story.
Yeah.
There's more to intelligence than just, how well it performs on a specific task,
You got it. And that's what makes this research so cool. We're exploring the edges of AI, looking for those ways to go beyond just the numbers, the scaling laws, and develop AI systems that are like really flexible and adaptable the way human intelligence is.
So we're not just trying to make AI better at like crunching numbers or whatever. We're trying to like understand intelligence itself.
Exactly. And one of the most promising areas is this idea of creating AI agents that can actually learn and adapt in really complex dynamic environments, more like how humans learn out in the real world.
Okay, so we're moving away from these AI models that are just like isolated and focused on one task. We're moving towards systems that can like actually interact with their environment, make decisions, and learn from experience.
Yeah, that's it. One study, they use this technique. It's called multi-agent inverse reinforcement learning, MARIL. It's a mouthful, I know, but they used it to train these AI agents in this cooperative setting. So they made this simulated environment where the agents, they had to work together to achieve some goal.
It's like AI team building, right?
Yeah.
Like they got to figure out how to work together.
Yeah, exactly. And the crazy thing is, these agents, they actually learned some really effective strategies, and they did it without even being programmed with the rules of the game. They watched these expert agents, and then figured out the reward function. That's the thing that guides their learning process.
Oh, wow. It's like watching little kids learn a new game by watching the older kids.
Right.
They figure out the rules by watching and trying things out.
That's it. And that ability to learn from just watching is huge.
Yeah.
We need that. If we want AI that can operate in the real world where the rules aren't always clear, where they're always changing, right?
Yeah, totally. So we're not just building AI that can follow instructions. We're building AI that can figure stuff out on its own.
Yeah.
Just by watching and interacting.
Exactly. And these MARIL agents, they actually did incredibly well. They were consistently better than other multi-agent learning methods, and in some cases, they even did better than the expert agents they were learning from.
That's amazing.
Mhm.
So maybe we're entering this whole new era of AI where intelligence isn't just about bigger models and more data, but it's about creating systems that can learn and adapt in ways that are way more dynamic.
Yeah, that's the idea. And this could totally change all kinds of fields. Robotics, finance, education. Imagine robots that can learn how to do complex tasks just by watching humans do it. Or AI tutors that can change their teaching style to fit each student.
It's like we're moving beyond sci-fi into this world where AI is just a normal part of our lives.
Yeah,
And it's helping us do all kinds of things we never thought possible.
right. And as we, wrap up our deep dive into these AI scaling laws and like what's beyond them, I think it's really important to remember that we're still just starting out. There's so much more to learn and discover.
It's like we've just started to make a map of AI intelligence, and there's all this uncharted territory waiting. And as we go further into that uncharted territory, we got to remember the ethics of what we're creating,
Oh,
right?
absolutely. We're building AI systems that are more and more powerful and complex. So we got to make sure that they're aligned with like our values
Huh?
and that they're used to help people. We can't forget about the risks, even though the opportunities are, they're pretty incredible.
Yeah, for sure. The future of AI, it's not set in stone. It's up to us to to shape it in a way that's good for everybody.
Yeah.
And that's a great note to end on, I think. That wraps up our deep dive into AI scaling laws and the crazy possibilities beyond them. I hope you enjoyed it.
It's been great exploring all this with you.
And until next time, stay curious and keep asking those big questions.